Hey there, welcome to the video discussion section 6.3, part 4, antiderivatives and the definite integral. So when we can't, let me read this question. How can we find the exact, not approximate numerical integration value of definite integral if it isn't an easy area? So for example, we have the integral from 0 to pi of sine x dx. Now, the way we've done this up to now, if you wanted to find the integral from 0 to pi sine x dx, and remember sine x looks like this, where here's pi, so I want this area, you know, excuse me. The way we would do is what we do in the calculator, right? And remember, the calculator is an approximation. And remember, we did a alpha window fn int. Okay. So and of course, when you do that, you know, you type this in the calculator, all that you see there, and you get 2 as your answer. But how do we do that to get an exact answer? So basically, analytically, without a calculator. Okay, geez, I can't write. Analytically, let me spell that a little bit better. Analytically. Without a calculator. Because again, when we do this, it's giving us an approximation. In fact, actually, if I go up to this part right here, remember we got 8.999999 for example 3, and we just rounded up to 9. The calculator was giving us an approximation there when it did the integral, when it did that integral. So let's talk about a simple example and how we can actually evaluate this integral more analytically without a calculator. So let's just say example 5, but that's okay. A particle moves along the x-axis with velocity 3 plus 2t. So what you're going to do is you're going to graph this. This is 3. T is greater than or equals 0. And let's calculate this as travel from 2 to 5. So 1, 2, 3, 4, 5. Okay. If you plug 2 in, I think you get 7. So obviously I'm a little off with my tick marks on the y-axis. And I plug 5 in, I get 13. So I want to get this area here. So we're going to first do this by using a definite integral and find the area under the curve. So let me get some highlighters out here. Maybe I'll highlight one area in green. And I'll highlight another one, say in orange. So if I want to find those areas, pretty simple. I'll call this A1, will be 3 times 7, or 21. This one here will be 3, or 1/2 times 3 times 6, so it'll be 9. So the answer is going to be 30. And again, we're just doing area. You can also define the area of a trapezoid too. Excuse me, if you want to do that. Remember, area of a trapezoid from back in the day is this times the height. This would be B1. This would be B2. And your height, of course, the altitude here is going to be 3. If you work that out, you'd also get 30 still. So anyway, geometrically, we see the area is 30. Now, part B is a big deal. because part B we're asking to use antiderivatives like we did in our previous unit. And remember, distance traveled, whenever your velocity is bigger than 0 and your time is bigger than 0, distance traveled is actually the same thing as displacement. Remember what displacement was? The change in position. So in this case, we're finding the change. And remember, position, we used S of t. So in this case, I'm finding S of 5 minus S of 2. And remember that velocity in terms of time is a derivative of position in terms of time. So we could say that S of t is the antiderivative of velocity. Since velocity is a derivative of position, then position is the antiderivative of velocity. So remember V of t again, our formula is 3 plus 2t. If I do the antiderivative, so you have to kind of think this one through, excuse me, is you're gonna have 3t plus t squared, because antiderivative of 3 is 3t, plus t squared, and you can put a plus c at the end, a constant. So S of 5, if you work that out, is 15 plus 25 plus c, which is 40 plus c. S of 2, if you work that out, that would be 6 plus 4 plus c, which would be 10 plus c. Again, the distance traveled, which is what we're being asked to find here, will be the same thing as displacement because our velocity is always positive here, so we don't have any negative velocity or negative positions to worry about. And change of position is just, you know, S of 5 minus S of 2. That'll be the distance we traveled from 2 to 5. So we found the position at S5, 40 plus c, the position at S of 2, 10 plus c by doing antiderivatives of velocity. So when I subtract these, 40 plus c minus parentheses 10 plus c, you get 30. So that's interesting. So looking at results from parts A and part B, we see that the integral of our velocity from 2 to 5 is no different than plugging 5 and 2 into the position function. And remember, I assessed you guys on doing antiderivative velocity in our last test. So this is not a coincidence. It really is a big deal. In fact, it's part of something called the fundamental theorem of calculus, which is what we're going to discuss next week. And it's a very, very important theorem. It's really kind of the whole essence. I know I keep saying that a lot, but it really defines the second semester. I mean, yes, integrals do, but fundamental theorem of calculus kind of brings it all together. Actually, it defines the whole course, and hence why you call it fundamental theorem of calculus. So what we're noticing is that when you do the definite integral, to evaluate, I'm going to type this in a text box and share it with you in just a sec. To evaluate definite integral, simply find the antiderivative and plug in the limits of integration. Then take their difference. That's how you evaluate definite integral. You simply find the antiderivative of whatever function you got, plug in the limits of integration, in this case 2 to 5, and take the difference. We will talk about techniques of antidifferentiation and a more formal mechanical technique next week. But for now, we can kind of gather that if you have 3, the antiderivative would be 3t because root of 3t is 3. If you have 2t, the antiderivative of 2t is t squared because the derivative of t squared is 2t. And of course, you got to put plus c as a general way. But then when you do the definite integral, because you have these c's occurring for S of 5 and S of 2, they actually cancel out. Whatever constant you have would be canceled out when you take the difference. So to kind of state this more generally and then do some practice, let's look at the next page. When you have the definite integral of f of x dx from a to b, you can say it's the same thing as saying this. I'm using a capital F instead of lowercase f, where capital F is any antiderivative of f of x, little f of x. So for example, and by the way, capital F of x, again, we say is antiderivative little f of x, and the derivative of the antiderivative gets you back to the original. So these kind of like undo each other in a way, or the kind of like inverses, which will be a huge point of discussion next week. So anyway, you have the integral from sine x dx, or sorry, from 0 to pi of sine x dx. Well, the antiderivative of sine x is negative cos x, because the derivative cos x is negative sine x, but you have the extra negative to make it sine x. So your antiderivative will be negative cos x plus c. And then sometimes what we do, sometimes we put this little like vertical line, and we put the limits of integration like that. But we could write this as capital F pi minus capital F0, where again, capital F of x is negative cos x plus c. That's the antiderivative of sine x. So then if you plug pi in, you have negative cosine of pi plus c. If you plug 0 in, you have negative cos 0 plus c. Again, capital F of b minus capital F of a is how you evaluate a definite integral. We're using the antiderivative. So that's why I did capital F of pi minus capital F of 0, since my limits of integration were 0 and pi. Well, what's cosine of pi? That's negative 1. So negative negative 1 plus c. And cosine of 0 is 0, so 0 plus c. And the c's cancel, you just get, I'm sorry, cosine of 0 I know as let me backtrack, sorry. I should redo trig. Negative cosine of pi is negative 1 plus c, because okay, backtrack one more time. Cosine of pi is negative 1. I'm doing negative of negative 1 plus c minus cosine of 0 is 1, but there's a negative attached to it, so it's negative 1 plus c. So negative negative 1 is positive, so you have 1 plus c minus negative 1, so plus 1 and minus that c. You get 2 straight up. So that was what we got in the calculator when we did this, using the numerical integration feature where we did alpha, window, and then picked option 4. And notice the c's cancel out in the subtraction. So in the future, we can choose c to be 0 for convenience and not worry about it when doing definite integrals. So you don't worry about c for definite integrals. That's because the c's cancel out. Now, we are going to talk about indefinite integrals when you don't have a limit of integration and you're just simply doing an antiderivative. You will need to put plus c, and we'll talk more about that next week. But for now, let's do a couple more examples and wrap up these notes. So let's look at this one here. What's the antiderivative of x? Well, antiderivative of x is 1/2 x squared, because if I take derivative 1/2 x squared, I get x. Antiderivative of e to the x is e to the x, so derivative of e to the x is e to the x. And I'm going to plug in 0 and 1. So basically you're doing capital F of 1 minus capital F of 0. Remember, capital F of x, the antiderivative, was all that. Well, if I do capital F of 1, I get 1/2 times 1 plus e to the 1 minus, if I plug in 0, 1/2 times 0 squared plus e to the 0. So 1/2 plus e minus, and then that just goes away, but e to the 0 is 1. So you get e minus 1/2. That's that one. And again, you can plug in your calculator and you'll get a weird decimal. And if you work out e minus 1/2 in your calculator, you also get a weird decimal. Those weird decimals will be the same. If you do the numerical integration of this in the calculator using alpha window option 4, or just type in e minus 1/2, those would be identical. Looking at one more, you have 1 over 1 minus x squared. Hopefully you recognize that the derivative of inverse sine of x was that. Hopefully you can see that. So the antiderivative of 1 over root 1 minus x squared is inverse sine of x. So what I'm going to do is, it's going to be capital F root 3 over 2 minus capital F of 1/2. That's going to be what this antiderivative is, this whole thing here. Or we write like this: inverse sine of x plus c from 1/2 to root 3 over 2. But we don't have to worry about the plus c anymore. It will go away. And you can assume it's 0 for convenience, as I was saying. So you're doing the inverse sine of root 3 over 2, because that's our antiderivative. So that's the capital F of root 3 over 2. Remember, capital F of x is inverse sine of x plus c minus inverse sine of 1/2. Well, inverse sine of root 3 over 2, I believe, is pi over 3. Excuse me. Pi over 3 minus pi over 6. So the answer is pi over 6. And there you go. And again, you could use your calculator to kind of check that out. And there's one thing about the calculator I'm just checking out here. I'm not sure. There's something about a calculator trick that does not making too much sense to me in my filled out notes. Anyway, nothing really to be worried about. Okay, that concludes the 6.3 notes. I'll see you guys in class tomorrow.